get started. So today's recitation is a review for the final exam. Before we do that, just a few comments on proxy lab, since that's due soon, based on what we've seen in office hours. So we mentioned this last week, but people are still making this mistake. Make sure that when you're getting back data from the server, you're using the, just like read line, or not read line. You're not using read line. You're using like read NB. And if you're copying it, you're using men copy rather than using read line or string copy. So make sure you're using functions that don't expect everything to be terminated with null bytes, because you will get null bytes in the middle of your data, not just at the end. Some people are still making that mistake, and it does make your proxy not work. And it might work on some pages and not others, is the thing. Also make sure that, if you're having issues, one thing to check is that you're sending the right headers, and also that you're sending the right GET requests, but also some people have been sending the right GET request but the wrong headers with it, and that can cause things to not work right. And let's see, what else was there? There's another common issue. Make sure you turn off, if you're using your proxy through Firefox, make sure you turn off Firefox's cache. Some people thought it worked because Firefox's cache had the pages, but it wasn't going through their proxy. And once they turned it off, they realized they actually weren't done yet. And then one last thing is, if you're having issues where it's like working in Firefox but not on the driver, one thing to try is to actually start up your own tiny server and connect to it through your proxy using curl, because that's what the driver is doing. And if you open up the driver file, you can see the command it's using to test. It might be an issue with how you deal with port numbers. In Firefox, you're always going to be using port 80 because that's the normal port, but the driver is testing things out on different ports. Some people have had issues with that. So just a few tips if you're still working on that and having trouble. But the focus of this recitation is just review for your final. So after Proxy Lab is due, the last thing you have left is the final. There's no classes this week on Tuesday or Thursday. So that's all you have left. So what I have here in the slides, so there's questions on 5 different topics, all of which are things that you could expect to see potentially in the final. Note that these aren't the only topics you would see on the final. The final, might cover anything that we've talked about this year. So don't think that you don't need to still remember stuff from earlier on, or topics in the second half that aren't here. This is just a subset of interesting problems, but all they are, these are just problems from the practice exams that are online, the same ones that you can already see. So before we do these, does anyone have any questions, specific questions from the practice exams, just general review questions, things you want to ask to review before I just go through these pre-selected ones for you?
Can I ask a question about proxy quickly?
Sure, if it's quick.
If you define a variable within your thread routine, or if you initialize it within your thread routine, can you pass pointers to it around it without any issues, I suppose?
So is it
It's defined locally.
a local variable inside your thread
Yeah, and then you pass it to other helper functions, perhaps.
that are
Pointer.
that are running as part of the same thread?
Yeah, they're like, well, you have other helper functions defined, I suppose, and then it passes to pointers.
Yeah. As long as you're still within the same thread, that's fine. Yeah, the whole thread gets its own stack, so the thread can see the local variables from any function within that thread. Any other questions? Has anyone started looking at the old exams yet? I know some of you did for the midterm, but I guess this is a bit earlier, so maybe you haven't started studying yet. Okay. Well, since none of you have specific questions, let's just go over these pre-shows and problems, because they're a good spread of different ideas that you'll need to be able to remember. Okay, so this first one, this is from Fall 2012, problem 9, about virtual memory. So Is this big enough that people can read it, or should I zoom this in a bit? Can you guys see this? No? Let's see, how do I zoom in? Okay, so what you have, you've got this setup. Let's move some stuff around. You've got virtual addresses are 20 bits. You've got physical addresses are 18 bits, and your page size is 1,024 bytes. And then you've got this, the translation look-aside buffer and a page table drawn out for you. The translation look-aside buffer is two-way, associated with 16 entries total. Okay? So what are we doing? Okay, so here's part one. Part one, we want to indicate the following fields in the diagram: the virtual page offset, virtual page number, and the TLB index and tag. So we've got our 20 bits. Okay, so can anyone tell me where any of these parts might be based on this information here? So let's start with just the offset and the virtual page number. So how many bits do we need for the offset based on these facts up here? What's relevant for calculating the offset? What is the offset used to do? I think. So yeah, so 1024 is the page size. So the offset is going to get us to a byte within that. So we need an offset that's big enough to address 1,024 different bytes. So how many bits do we need to address 1,024 bytes? 10, exactly, yeah. So just log base 2 of 1,024 will give us how many bits we need for the offset. So the VPO is going to be, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is by 9 by 10. So this part here, this is the virtual page offset. All of those bits are that. Okay, and so then what bits are used for the virtual page number? Do we remember how these work? So remember the what? 5. So let's remember how these are structured. So we have the address, and it's split into two components, the page offset and the page number. So all of the bits that aren't the page offset are used for the page number. And then remember that the page number was split again into the two TLB pieces. So there's going to be some overlap in these categories. So then the rest of it is the virtual page number. So the virtual page number is bits 10 through 19, and the virtual page offset was 0 through 9. We got that from 1,024. Okay, so then what we know is that the TLB is two-way set associative with 16 entries. So what does that mean? That means there's eight sets, right? 8 sets with 2 lines each. And we can see that, just by looking at the picture. That's we can read that off if you forgot what those meant. Okay, so now we need to figure out how many bits, which bits are used for the index and which bits are used for the tag. Okay, so if we have 8 sets, how many bits do we need for the index? Very similar to what you did before. 3. Yeah. Right, yeah, just log base 2. So, anytime you need to address n things and you need to know how many bits you need to do it, it's log base 2 of n is how many bits you need to address n different things. So we need to be able to address 8 sets, so that gives us 3 bits are being used for the index here. So these 3 are the TLB index bits. That's 10 through 12. Okay, so then what does that leave for the tag? Well, it just leaves everything else, right? The tag is whatever is not used by the index. So then these bits This is what, 13 through 19 is the TLB tag bits, okay? So these are our different pieces. So does everyone sort of see where we got those numbers from? There's another split right here. Yes? Okay. So that's part one. Now part two. So now we have the physical address, which is only 18 bits wide. And we want to just label the physical page offset and the physical page number for it. So I'm not even going to draw this one out. Let's just talk through it. So what do we know? What's the key fact about physical page offsets and virtual page offsets? How does this always set up? Did I hear it? I think I might have heard it. They're the same, yeah. We always make them the exact same size. That makes things really easy because that means to translate the offset, we just copy it down. We don't have to do anything to it. So we have 18 bits, and if they're always the same, that means we're still using 10 of them for the offset, and that means the other 8 are the page number, because that's what we have left over. So that's pretty easy. Once we have the virtual page offset, physical page offset is easy. Once we have physical page offset, physical page number is easy, because there's only one thing that you can do. Okay, so now this is the more interesting part. So we've sort of just labeled this diagram. You filled in all the boxes on the exam server. Oh, but I guess I should have mentioned the exam. In case you didn't know, the exam's going to be very similar to the midterm. You've signed up for times. You get a longer slot now than you got for the midterm, but you'll come in, you'll sit down, you'll have the same thing with problems that you'll fill out on the computer. Same sort of setup. Same, you can have the note sheet. Again, just like before, it's all pretty much the same except just more topics. Yeah.
You have one or two note sheets?
What?
Can you have two note sheets or one?
It's just one still, unless we said two somewhere. I don't think we said that. But front and back, yeah.
There's always front and back.
Yeah. Okay. So now let's do the second part of this problem. So now we want to actually translate a virtual address into a physical address based on those tables we had above. Okay, so I'm just going to let's just reuse this guy here. Okay, so what we have is that our virtual address is 078E6. And all of these numbers are in hex. It's 078E6. Okay, so the first thing we need to do is we need to actually fill out the bits for this number. Right, so we did this before. We did this same thing when we were reviewing caches for the midterm, remember. We're going hex to binary. Hex to binary is pretty easy because we can consider it just one character at a time, which is nice. So we know that we get 4 bits per hex character. So what's 6? 6 is 2 plus 4, right? What? 0, 1, 1, 0. That. So 0, 1, 1, 0 would be, no, you're right. Confused myself there, right. 0, 1, 1, 0, okay, good. And now E, so what's E? E is 1 less than F, and F is the number with all 1s. Just 1, 1, 1, 0. Okay, now 8. What's 8? 1, 0, 0, 0. And what's 7? 0, 1, 1, 1, just 1 less than 8. And then 0, 0 is pretty easy. 0 is just all zeros. Okay, so we've gotten the bits for this number. That's not too bad. And since I copied them into the old diagram, we already have them split up into the correct pieces too. So now we want to actually figure out the virtual page number, the index, and the tag for a translation look-aside buffer, and then we'll use the tables to figure out what the buffer lookup is and what our page number is. Okay, so our virtual page number is this part of it, right? That's what we labeled on the diagram. So let's figure out what this is. I think it wants us to put it in hex. Yeah, it wants us to put it in hex. Now we got to translate this part of the number back into hex. Okay, so we've got 1110. So what's 1110? That's just E, right? You should be able to do these translations quickly. You don't want to spend your whole exam figuring out, binary to hex. This is something that you should be able to do relatively fast. Okay, so 1110, and then we've got what? 0001. That's just 1, and then zeros on top. So it looks like our virtual page number is 01E. Okay, and then our TLB index and tag. So what was our index? Our index we said was these 3 bits here. So we've got 110. What was that again? That was 6, right? So this is the VPN. This is the TLB index, and then the TLB tag. So the TLB tag is this remaining part. What's this? What? Yeah, it's just 3. Okay. So now we've gotten those. What we want to do is see, the next question is this a hit to the translation look-aside buffer or not? Okay. So this is where we have to go back up to the table. Okay, so what did we get? We got the index was 6. We got the tag was 3. Is this a hit? No. Not according to this table. 6 has tags 1B and 0 in it. Neither of those are equal to 3, so it looks like this is a miss. Okay, so TLB hit. B hit. No. Okay, and then let's see, page fault. So now we want to know, is this going to be a page fault, or will we be able to look it up? So can anyone tell me, well, when does a page fault occur? What about this table would correspond to a page fault occurring? It's when it's not in there. So a page fault would occur if it's not in there. A page fault is like a cache miss in the virtual memory system. It's when we look it up and we can't find it. So what do we have? So we have, let's see, VPN 1E. Okay, and what does it say? Oh, good. We have something valid for 1E, and it's actually physical page number 57. Okay, so that's good. So page fault, no, it was valid. So if we looked it up and it was not valid, then we would have a page fault. But it's in there, so we got physical page number 57. So then how would we actually construct the full physical address? Is then we take 57 and we put it back on to this same offset that we had before and rewrite that out as a hex number. But does it ask for that, or does it just want the it just wants the physical page number? Okay, so we don't actually have to do that. Oh, no, we do. It's the next part. Never mind. We do have to write it out. Okay, so how do we write this out? So we know from before, okay, it's not going to ask us to put it into hex, but we know from before that we have this copied over, so we'd copy these down. That's pretty easy. Even if you've messed up the rest of the problem, you can get this part right, because this doesn't depend on any of that lookup in the table or anything. As long as we translate it from hex correctly, that will be okay. And then we just want to translate 57 into the top bits here. So 7 would be 0, 1, 1, 1, and then the 5 would be, let's see, 1, 0, 1, 0, and then that's all of our bits. Right, so does that make sense how we got from the information up at top and the 2 diagrams all the way to the actual physical address in the end?
I have a question. So for the physical address, just to be clear, so the 57 would go in the VPN?
So the 57 goes in the PPN, yeah, which is bits 10 through 17.
Okay, and then the VPO stays the same.
And then the VPO and the PPO are equal, yep. And that will always be the case, is that VPO and PPO are always the same, you just copy it down. Which is, I mean, it's good in the hardware because then it's pretty fast. Copying is much faster than changing things around. Okay, so now we've got, okay, another one. Same thing, except just a new virtual address. So let's see if we can save this diagram and just work it out again. Okay, so our new address, these are all going to change. Our new address is 04AA4. 04AA4. Okay, so what is 4 in binary? As 4 bits. 0100, exactly. Okay, and then A, so A is the equivalent of 10. If you're in decimal, anyone know? 1010, yeah. It's actually just like 2 tens if you want to be really abusive and read it out as a decimal notation. Okay, and then we've got another A, 1010, and then another 4, 0, oops, 0100, 0, and then it was 0 up top, so 4 more zeros. Okay, so now we've got the bits, the virtual address for this problem. Okay, so now we just need to do the same thing again. Virtual page numbers, so the virtual page number we got by reading off this stuff here. So what is it here? So this is a 2. And then what's above it? Just a 1. So the virtual page number is hex 12. Okay, and then what's the next part? And then we want the TLB index and the TLB tag. Okay, so what's the TLB index? Any ideas? 010 is 2. Okay, and the TLB tag, hey, look, it's also 00010, 2. Okay. So now we've got the index and the tag, and we want to know if it's hit or not. So we're going to go up to our translation look aside buffer. And our buffer says, if you have 2, and you have 2, which is what we have, so we have index into the set is 2, our tag is 2, and it's valid. That's important. If this wasn't valid, it wouldn't be a hit, but it is valid. So our physical page number is 68. So we didn't page fault because we were able to actually find it even in the buffer. We didn't even have to go to the page table. So no page fault, and what was it? I forgot already. 68. 68. Okay, so that is our page number. So now what we would do to just finish off the problem, the last bit would then to be read out the bits of the physical address. So we'd copy these down because the virtual page offset is the same as the physical page offset. And then we translate these into bits 10 through 17. And then we'd have our new number. So that's the end of that. Oh wait, no, yeah, that's the part we just did. Okay, good. That's the end of that problem. Yes?
So if it's not in the page, or yeah, if it's not in the page table, then it's a, you described this earlier, it's a miss.
So yeah, so then it's a page fault.
And
So
then you can't create this address in that case.
right, yeah. So then the kernel has to go and go get you some virtual memory. And so the instructions, I didn't read them carefully, but it said if there was a page fault, we would just enter dashes for the rest of the problem because we don't have enough information here to solve it.
Okay. Does that mean you put dashes with the VPO too, or can you keep the VPO and just dashes?
So we technically know that the VPO will be the same, but this problem just said you don't have to. You can just then you're not done with you're done with the rest of the problem. Yeah. What we would normally get back is once there's a page fault, we would update the page table. The operating system would take care of updating the page table, and then we re-execute that instruction again with that memory access, and now it's in there. That was something we talked about when we talked about exceptional control flow. Okay, so then maybe we should we check and make sure that we got it right? Okay, so which one was this? This was problem 9. Okay. 9, let's see, 68, yeah, that's what we got there, 57. Yep, yeah, it looks, okay, it looks like we got it right. That's good, okay. So we finished one problem on our exam, like 5 more to go, or however many end up being on it. Okay. So I/O redirection. Okay, so this is from the spring 2011 exam. It's a little bit big, okay. So I/O redirection, okay, so we have a file called numbers.txt which contains the digits 0 through 9 in order, okay? And we're assuming that read calls are atomic with respect to each other. So like once you start a read, you'll actually read that thing out. You're not going to start another read halfway through and finish that guy first or anything weird. Okay, and now we have this little bit of code, read and print 1, and what does it do? It reads a single character from the file descriptor, and it prints it out, and then it flushes to standard out so you don't end up with things like getting buffered and not printed out right away. So all it does is it's just going to give us the next character in the file right away. Okay? And now what we want to do is say, what are the possible outputs of the following code? And so what do? We open a file, and then we open another file, we dupe 2 to make file 2 and file 3 the same. So if you remember how dupe 2 works, if we do dupe 2 file 3 file 2, now file 2 is a file descriptor pointing to the same thing as file 3 points to the same thing as file 2. No, file 2 points to the same thing as file 3. I always get it backwards. But what that means is, so okay, let's draw out the diagram. We can erase this now. So if you remember, oh, this said save. Oops. It's too late. Okay. So if you remember what we had, so we had this, and we had these diagrams. This is sort of like, so we've got these file descriptors. So we've got 3 file descriptors, and we've got one file. This is numbers.txt. And then in between them, we had the piece of information that kept track of where we were in the file and such. Remember that? So what do? We open up a file. So we're opening a file, so we're going to have file descriptor 1 pointing to this file information, which ultimately goes to the file on disk. And then we do another open. So we've got this guy, which is pointing to the same file here, but it's separately keeping track of the position in the file, if you remember the information table for the file. And then we do a dupe 2. So if you remember what dupe 2 does, is it duplicates the file descriptor to point to the same information. Okay, so this is sort of the diagram of what's going on. Okay, so what's going to happen when we go through these? It looks like it's actually pretty deterministic, doesn't it? There's no like signals or forking or anything going on. So it looks like we'll actually only get one output. We just need to figure out what it is. Okay, so we have read and print 1 from file 1. So what's that going to print out? Remember that this file contains just 0 through 9. What? So we're just the read and print 1. If we go back to the code, it reads exactly 1 character. Right. Okay. So we start by printing 0. Okay. And now we do read and print 1 on file 2. So what does that do? It also prints 0. Right. Because these two descriptors are keeping track of their position information in the file separately because we opened them with different calls to open. But now we do read and print one of file 3. And file 3 and file 2 share the same information because they use dup2. They're separate file descriptors, but they're sharing the same information about where they are in the file. So now what do we print out? Now we print out 1, yeah. Okay. And then now we do file 2 again. So 2. And now we do file 1. 1, yeah, because remember file 1 is keeping track of its position information independently. And now we do file 3. 3. Right, okay. So file 2 and file descriptors 2 and 3 are essentially the same thing. They're, every time you do a read from one, it's updating the position across both because we've used dup2 to make that copy. And then file 1 is independent of them and it's doing its own thing. So then what we get back is 0, 0, 1, 2, 1, 3. Okay, so that's part 1. It's not too bad. Does everyone sort of see where we got that from? Okay. Drawing out these diagrams is useful in problems like these to see where things are shared. Okay, so now we've got part 2, which is same thing. We want to write out all of the possible outputs, but it's a bit more complicated now. So what we do, we're opening 2 files. We do the dup2. That part's the same. So it is the same diagram as it was here. But now what we're doing is after we do 2 reads, we fork. Okay, so we're going to fork. So let's just work through it and talk about the fork once we get to it, and start thinking about what different things can happen there. Okay, so the first 2 reads are gonna happen first, no matter what, right? We have to go through these 2 guys to get to the fork. So we read from file 1 and then we read from file 2. What does that give us? 0, 0. Yep. 0, 0. Same as before. Okay, and now we get to a fork. So we fork, and let's look at, let's think about what the different orders that are possible are when we do the fork. So we do a fork, and we have if not PID. So was that going to be the child or the parent? So in fork, what does the parent get back? What gets returned to the parent and what gets returned to the child? So the child gets 0, and the parent gets the PID of the child, which is something that's non-zero. So now we're abusing C's non-distinction between bools and ints, and we're knotting that value. So if we have something that's 0 and we knot it, then we get 1, which is true. So if this is the child, it's true. So this is the branch for the child, and then this is the branch for the parent. Okay, everyone see that? So if we execute, so let's read through it a little bit before we start thinking about the different orders. So the child, what it's going to do is it's going to print out a thing, it's going to close the file, open it back up, and print out another thing. The parent is going to wait and then print out 3 things. So what does that mean about the ordering of the child and the parent? So normally, what we know is that when we do a fork now, the parent and the child are going to be interleaved arbitrarily, unless we do something that synchronizes them up. And wait is one of those things. So now what do we know about the order of the reads from the child and the reads from the parent? The child will go first. Yeah, everything from the child is going to execute before the parent executes. Okay. So let's see what the child does. So the child does a read and print 1 from file 3. Okay, so well, actually, maybe we should we should maybe draw the diagram for what now the child looks like, shouldn't we? So what does the child look like? We get new file descriptors, right? And we get Do we get new information about where we are in the file, or is this shared? Would be the same, right? Yeah, okay. So now we get the child has its own file descriptors up here. Okay. So, okay. So what happens? So the child is going to print from file 3. So file 3 was at 0, so that's going to print us 1, right? And now we close it. Okay, and now we're going to open it again and print again. So we just reopened it. So that means we start at the beginning, right? So now we're going to print another 0. Okay. Print another 0, and then we print from file 3 again. So remember, the child isn't done executing until we get to the return over here. The child is still going. So now we print from file 3 again. Okay. And now what is the parent doing? Okay, so now the parent can finally execute because the child has died. And so it's printing from file 3. Now, is it getting the file 3 that we opened over here, or is it the file 3 that was the old file 3? Yeah, it had the file 3 from before. So what does that give us then? 2. So remember, this is where we forked. So 1. 1. Then file 2. 2. And then file 1 now. 1. And now file 3, I think. 3. Yeah, okay. Do we see where we got that from? Yes.
Okay, so when you close file 3
Mm-hmm.
and then open, and then you reopen it,
Yep.
does that create a new descriptor or?
So yeah. So what's going on over here is we had file 3 down here in the child, and we said, okay, let's close this, which gets rid of it. And now we say, okay, let's actually open up file 3. And so we create a new guy pointing to file 3. Or a new file descriptor 3 that points to the same file, but it's a new open. So now we're not sharing with the other file descriptors anymore.
Okay.
Does that make sense?
Yeah, so anything that descriptor has done on it doesn't affect the parent. Basically.
Right, yeah, now this descriptor has no relation to the parent because it's the new entry, the new information. Okay, so let's see. This was... Now, are there any other orderings? So we got n ordering. Is this the only one? Yes, because we have the weight, which means that there's only one ordering that the child and parent are going to execute in. If we didn't have that weight there, then we'd have to do all the interleavings of the prints from the child's and the parent, and that would actually be a lot and be really annoying. So I'm glad that that's there. That makes the problem simpler. So we could, we can peek and check, see which problem was this. This was spring 2011. Let's see if we got it right. It's problem 6. 001, 01. Oh, it looks like we messed it up slightly. This should be 234. So we got off somewhere. Okay, let's figure out where we got off.
I think it's off because when you did the file 3 descriptor for the
Mhm.
child or the parent, you didn't advance it because of the file 3 read in the child thing.
The one.
Like when you did the first line.
This one?
Yeah, you didn't advance it for yeah.
Okay, yeah. So we forgot about this one. So this one does advance it in the parent because this was the same file descriptor that they shared before we closed it and opened it again. Okay, so people in the back paying attention figured out the mistake. Good job. So yeah, so this was actually supposed to be then 10123114. So this is from file descriptor 1, was unaffected by that. Okay. So these are tricky. Be careful on them. They're easy to mess up if you're not paying close enough attention. Drawing out diagrams is certainly something that might help. Okay. So threading. So this is again from 2012. Okay. Let's see. So we've got a simple concurrent program. The main thread creates two peer threads, passing each peer thread a unique thread ID and waits for them to terminate. Each thread prints its ID and then terminates. And we're trying to implement this. Some are incorrect because they contain a race on the value of my ID. And other than that, they're going to be correct. So we're looking for races on the value of my ID. And it's just going to be code and then yes or no, does it have a race? And I guess it got cut off what the grading criteria is, but it probably says something like, I don't know what it says. Maybe it says if you get it right, +2, if you leave it blank, 0, if you get it wrong, -1 or something, so that you can't get points just by guessing. But okay, so let's figure out if these have races or not. Okay, so here's the first one. Let's see. Okay, what's it doing? So foo. Okay, so does this one have a race on the value of my ID? So what we do is we go through, we malloc 2 ints, and then what we're going to do is we're going to pass those ints in to our function that we're using for our threads, and they're going to, those 2 malloc spots in, and they're going to put my ID in that spot and then print it out. Does that have a race? No. Right. So this is maybe this is something that you did something similar to this in your shell lab. Certainly a thing you could have done in shell lab to deal with concurrency issues. So like all we're doing here is we're saying, okay, let's make 2 things, 2 spaces, and we'll put ID1 in this one, and we'll put ID2 in this one, and then we'll print them out. And it doesn't matter which what order things happen in here because they're working with disjoint spaces. They can't overwrite each other. They can't clobber each other in any way because they're mutually exclusive accesses to this memory. So there's no race here. This one's good. Does everyone see that? Why there's no race? Right, yeah. We malloced 2 separate spaces for them, and now each thread has mutually exclusive access to the memory it's using. The thread 2 isn't going to touch this memory. Thread 1 isn't going to touch this memory. So it doesn't matter what order they happen in. They can't interfere with each other. The issues with shared memory and threading happen when you have 1 bit of memory that's being touched by multiple threads. That's where you start getting issues. Okay, problem B. So does the following program contain a race on the value of my ID? What do we do here? We're stack allocating an array now, and we're putting in the addresses of it, and then we're printing it out. Does that have a race? Yes, why?
Because you're already passing the address of I, so if you get to the place where you're actually saying my ID equals dereference int star argp, and you already got to the next iteration of the for loop, then the I could be 2 even though you're working with thread, or I could be 1 even though you're working with thread 0.
See, passing. Right, yeah. Exactly. So the issue is that we're not disjoint over here with this I. Okay. So that one's not safe. How about C? Does this one contain a race? So here we're doing stack allocated again. But we're passing an I instead of the address of I over here. Does that fix our problem? Well, we're just casting it to a pointer, and then we know inside our function that it's not actually a pointer. We know that it's really just an int. Does this one have a race? No? Let's see. Yeah, I don't see one, so I think this one's good. Because we're not using the address of I, so we're not potentially sharing memory anymore. We're just passing in I, which is not going to be changed. Okay. Well, actually, we're out of time. There's two more. If you enjoy these, you can go and figure out those. If you don't enjoy them, you can do it anyway because it's good practice for the exam. That'll be it. Congratulations on almost being done with 213. Thank you for coming to recitation. Good luck on the final.
Will the final have like 10 questions?
I mean, it should be longer than the midterm. I don't know exactly what is planned to be. Maybe, yeah, maybe
Maybe
8,
you guys
9.
can take it, but the problem is you are not gonna work on it.